Thinking Aloud. Conversations on the leading edge of knowledge and discovery with psychologist Jeffrey Mishlove.
Hello and welcome. I'm Jeffrey Mishlove. Today, we'll be exploring interpretations of quantum mechanics. With me is Dr. Ruth Kastner, who is a physicist and a philosopher and a specialist in the foundations of physics. She's on the faculty of the State University of New York at Albany and is also a research associate at the University of Maryland. In addition, she is the author of the Transactional Interpretation of Quantum Mechanics, From Reality to Possibility, and also the author of Understanding Our Unseen Reality, Solving Quantum Riddles. Welcome, Ruth.
Thanks very much. It's great to be here.
It's a pleasure to be with you. Quantum mechanics is something everybody has heard about, but very few people seem to understand it seems
Right.
to me. And as I read your work, it gets even more confusing in the sense that there are different interpretations of quantum mechanics competing. And they're very different interpretations. So let me ask you, why are there so many interpretations, and why does quantum mechanics need to be interpreted at all?
Well, quantum mechanics boils down to a set of rules, really. It was arrived at almost haphazardly because when physicists around the turn of the 20th century were trying to understand the behavior of atoms, which they knew existed, they found that their classical laws were breaking down, and they just, to their dismay and surprise, these laws just didn't work for them anymore. So a group of very inventive physicists, among them Heisenberg, Schrödinger, Bohr, they're all very well known, Einstein also, very cleverly managed to use the Ludwig Boltzmann's idea of atoms to continue to explore what other sorts of principles could they bring into play?
Right.
And by using this concept of unseen atoms and applying probabilistic concepts to them, they were able to arrive at a set of laws that worked, a set of rules for calculating the results of measurements and processes that they would perform in the laboratory. But to this day, that structure, that quantum theory, if you will, it remains a kind of a mathematical formalism that works very well, has a set of rules, and it predicts what we see in a probabilistic sense, but it has a structure that doesn't lend itself easily to a realistic understanding of reality.
Now, you mentioned unseen atoms. Is it still the case that we have yet to actually observe an atom directly?
Well, you know, people might debate about that question. Some people might say yes, others might say no. I would be one of those who say that we can image atoms, however it's indirect. So we can expose them to certain modes of detection and measurement, and we get images where we feel like we're seeing, oh, look, there's a bunch of atoms all clustered together. But what we're really seeing is atoms exposed to our particular way of interacting with them. So it's indirect. In my view, it's an indirect corroboration that atoms do exist.
So in other words, one of the paradoxes of quantum physics is that we think of atoms as the fundamental building blocks of matter. What could be more real than an atom? And yet at the same time, we haven't directly, and maybe can never directly, observe an atom.
Yes, it's very paradoxical because I don't know if you've ever seen, there's this film called Powers of 10.
Oh, yes.
Yes. Well, they take you way out by larger and larger orders of magnitude. You get the whole universe shrinking away.
In 40 jumps.
Right?
The universe in 40
Which
jumps.
is almost easier to understand than when they reverse the film. And then they take you back to the young lady in Central Park or wherever she is. They start going in and suddenly we're like, where did everything go? everything seems to have disappeared. So that is the fascinating mystery of quantum mechanics. That
in fact, atoms, as I understand it, are mostly empty space.
Right. If you go in, they try to zoom in and they say, well, let's see, we found the electron cloud. Now let's keep zooming in, and nothing happens, and nothing happens, nothing happens, and then there's this nucleus coming up at you, right?
Yeah.
So in a way, and we don't even really, that's just a representation of what we think the nucleus looks like. No one's ever gotten their camera in there and said, I've got a shot of the nucleus.
Well, when I was a child in school, we learned the Niels Bohr model of the atom. It's like a little solar system. And every school child is taught that that's what atoms are like. And yet I understand from the perspective of quantum physics, atoms are really nothing like that.
That's correct. They really are not, it's not accurate to think of them as a little ball with other little balls orbiting around. So it's very insubstantial in a sense.
So this would be the beginning of interpretations of quantum mechanics that are useful to a point, but then of limited value thereafter.
Right. I mean, since we've all grown up in a classical world using our five senses where things are very concrete and we see things that are very well defined and determinate, we expect, in order to understand something, we expect to have that kind of picture, to be able to draw a picture or to visualize something. And this is where quantum mechanics fails us in a sense. It kind of lets us down, because every time we want to build a little model, a tinker toy model, it just fails, and it clearly doesn't work. So in a way, the smaller the distances we're dealing with, the less substantial and well-defined our objects are.
It's a paradox in that we're looking at the very basic building blocks of matter, but they're almost entirely insubstantial.
Right. And in fact, in one of my books, I think it's the first one, I'm not sure, I mention that, and in fact it's the second one for the layperson, that paradoxically the clouds of possibility, if you will, that are the electrons bound to the atom, to the nucleus, are pure possibility in a sense. And yet, without that strange behavior of the possibilities, we would not have the stable matter that we do. So it's, in a sense, those apparently insubstantial possibilities are the most potent thing in the world, because they form this rigid matter. And without those, everything would collapse in on itself.
Possibility clouds.
Right.
Now, we're talking about different interpretations of quantum mechanics, and I know there are quite a few. Do they all agree on this point, that possibility clouds underlie the rest of physics?
Well, no, they don't. One notable exception is the so-called Bohmian theory that that proposes that there really exists a tiny hard particle corpuscle that does exist and is sort of pushed around or guided by the more insubstantial wave function that is sort of the possibility. So that interpretation proposes that you have both things. I don't happen to agree with it, but that's one of the interpretations out there.
Well, many years ago, I did interview Nick Herbert, who was one of the people who inspired your work, I think, about his book Quantum Reality, and he pointed out at that time there were 5 or 6 major interpretations of quantum mechanics, and every one of them resulted in a paradox of one kind or another.
Well, yes. If you look at every interpretation, you're going to end up with, there's a cost benefit. It depends if you're looking for instance, people who like the Bohmian interpretation are missing the idea of solidity. They want to get that back. So they say, let's say there's really a particle there that provides that missing solidity. But there are certain drawbacks with the theory in that it has a little bit of tension at the relativistic level, which gets rather technical, but you have to say there's probably some preferred reference frame, which in general, in relativity, you don't want to say that any particular reference frame is privileged. So there are those issues. There's the so-called many worlds theory that I've argued has certain problems where it says it addresses the measurement problem, which is a kind of another topic. But there are obviously many many difficulties and challenges in quantum
and
theory.
And basically the many worlds theory, I think it's the Everett Graham Wheeler many worlds theory, suggests that there are maybe millions of other universes that are, every possibility represents a different universe.
Right. So it gets to be a very big picture. The basic problem, as I've argued, is that it's hard to say, or I would argue impossible to say, that the universe branches in a particular way. So what we want is, for instance, in the Schrodinger cat experiment, most people understand that there's a paradox where we have a cat that's both alive and dead.
Yes.
And the many-world solution to that would be to say, okay, there's one world in which the cat is alive, and there's another world in which the cat is dead. And that's called a basis, saying that's the way the world splits. But unfortunately, it's not that simple, and there's no clear way to say that the universe splits in a different way, in which in one world you'd have a crazy cat superposition, and in the other world you'd have a different crazy cat superposition. So that's one of the problems with that interpretation.
And the Bohmian interpretation, to which you referred earlier, we should say was developed by David Bohm.
Right. Interestingly, it was developed by Bohm and his associate Basil Hiley, who's still living. And Hiley does point out that he and Bohm, after several years, eventually moved away from that particular idea of having the corpuscle as what they call a beable, something that's not just an observable, but something that really exists. They ended up, after several years, deciding that really wasn't going to work, and they sort of moved on. But meanwhile, many people have stuck with that.
So you've got early Bohm and late Bohm.
Right, and the late Bohm isn't really Bohm. I mean, well, late Bohm went off in a different direction. He was exploring other issues related, but he didn't continue to promote this idea that there were corpuscles, but other people still do.
There is a standard interpretation to which most physicists and philosophers of physics, I believe, subscribe.
Right. That would probably be, and someone might disagree about how to characterize that. I guess the main feature of it would be to try to refrain from imputing particular realistic visualizations to the theory, and to just say we have the so-called the Schrodinger equation, which tells us how a quantum system evolves, and then we have another part of the theory called the Born rule, named after Max Born, who kind of arrived at it as an educated guess about how to figure out the probabilities of an outcome when we make a measurement. And that apparatus is standard quantum mechanics, and
Isn't that also called the Copenhagen interpretation?
Well, actually, the Copenhagen interpretation goes a little further than that in being more interpretive.
Okay. So the standard interpretation, it's one that physicists sometimes would call "shut up and calculate."
We could say that, perhaps. Yes.
In other words, do the calculations.
This is
they
the theory,
work, and don't worry about what they mean.
Right. And there are differences of opinion. Someone may say, no, that's not the standard interpretation. That's all part of where we are. So,
But the Copenhagen interpretation, named, I presume, because Niels Bohr was in Copenhagen.
And Heisenberg as well was collaborating with him, but primarily Bohr, yes.
And so that interpretation goes a little further than the standard.
Yes, it does. Bohr was trying to understand the meaning of quantum mechanics. He ended up seeing the meaning of quantum mechanics as telling us about observers. So in other words, for him it was very observer dependent. It was very knowledge dependent. And he ended up saying that we can infer that nature has these complementary aspects. So it's also called complementarity. I mean, you will get scholars who will say, no, complementarity is different from the Copenhagen interpretation. So we'll take take everything I'm saying with a grain of salt, as it's all debatable in terms of how to classify these things.
We're dealing with fuzzy boundaries here, which
is
probably an important thing to observe because quantum mechanics itself is rather fuzzy.
Right. So the state of the discussion still has these kind of overlapping categories.
But by bringing in the role of the observer, in other words, words, saying that we don't know where a particular particle is specifically located until it's been observed. That sort of opened the door for a wide range of theorists to begin to look at the relationship between physics and consciousness.
Absolutely, definitely. Now, I'm going to dispute that in a while,
yes.
but there was definitely, because of the fact that the theory just seemed to tell you what you were going to get probabilistically when you do an observation, and people weren't sure what it is that constitutes an observation or measurement. All they knew was that the system seemed to be described by these strange objects that we are having trouble visualizing. But we do know that when we make an do an experiment, we see a particle, or we think we see a determinate result, instead of this whole list of things that might happen. So that's what made people think that perhaps their observation has some crucial role to play.
In other words, quantum mechanics is based on, as we just said earlier, probability clouds.
Right,
or
I would
Schrodinger
say.
psi waves is another way to look at that.
Yeah.
But actually, when you observe, when you make an observation, you don't see a probability cloud. You see a particle, or you measure a field.
You measure what tells you a position of where a particle went, or perhaps a momentum, or you see an interference pattern. But you definitely, if you're going to measure a cat, you always find it's either alive or dead. Hopefully not dead.
Well, of course, that's an experiment that's never
that's
really
right.
been
That's
done.
only a thought experiment, and it
For
actually
all
wouldn't
you cat
work.
lovers out there.
And I explain in my book why that would never happen anyway.
Yeah.
So, yeah.
But the notion is that something happens where the equations, the probability equations, seem to overall, on a statistical sense, they work out accurately. But any given observation, well, it's just like throwing a dice.
Right.
You know,
and you will get an answer.
You will get an answer, and each die comes up approximately 1/6 of the time. But you never know in any given instance until you actually throw the die and look at it what side is going to be face up.
Right.
And quantum mechanics works much that way.
Right. And in principle, it cannot tell you, although the Bohmians might say it can. They say that's where the corpuscle is, and that's what tells you why you got that outcome.
Now, there is something called the hidden variable theory. Is that what the Bohmians...
That is a form of a hidden variable theory,
In other words, if only we knew what these hidden variables were, everything would be deterministic.
Right, exactly. And so technically, according to those theories, everything is deterministic. And the only thing that appears to give rise to probabilities is our ignorance. Right, so it's like an ignorance-based probability.
Now, you, of course, favor the transactional interpretation, which is, I'm guessing, one of the least known of
At
these.
this point, yes, it's becoming more known, but it hasn't been considered one of the mainstream interpretations.
And it's based on the idea, if I understand it correctly, of a certain amount of signaling coming both from the past into the present and from the future into the present.
Yes, in a way. What the transactional interpretation does is it accepts the usual solution to the Schrodinger wave equation, which is future-directed, but in addition it also makes use of what's called the advanced solution, which is past-directed. And that seems very counterintuitive, and it's often viewed as unphysical.
Yeah.
And so that's why it hasn't been as widely considered as the other interpretations.
But I gather that a big part of your work has to do exactly with this. It's a metaphysical question, ultimately, is what is the ontological status of these non-physical entities that keep cropping up in quantum physics?
Right. I'm very much interested in trying to look at the theory and say, in my view, the theory works so well. Why does it work so well? For it to not be a complete mystery or coincidence, it's probably describing some process that's going on in nature.
Yeah.
I think that's a natural inference. Now, the problem is that what it's describing is not really picturable. It has to be something that's sub-empirical in the sense that we can't observe this process. We can't get out our telescope and go, oh yeah, I see that going on. We can't do that.
The very idea that empirical science can acknowledge a sub-empirical realm seems fascinating to me.
Well, it is a challenge. And as a philosopher of physics, I can sort of do this exploration. I'm comfortable about doing this exploration. Many physicists might feel that this goes beyond the legitimate bounds of empirical science.
Yeah.
And in a sense it does. However, if you look at many of the great physicists, you look at Einstein and Bohr and so on, they constantly talked about ontological, metaphysical, if you will, issues. And they were aware that those issues underlie scientific exploration. So basically, if you think it as a scientist, you're refraining from indulging in metaphysics, then you don't know what your metaphysical assumptions are. So at least you have to know. And arguably, Boltzmann himself was dealing with metaphysical, sub-empirical concepts when he proposed atoms.
Ludwig Boltzmann.
Yes. I was thinking of Max Born, so that's where Max comes in.
Who proposed in the modern era
exactly
the existence of atoms. Of course, the ancient Greeks had a similar idea.
Sure, right. So it wasn't entirely new. But he brought it back in and used it as the basis of a very quantitative theory, the kinetic theory of gases. And of course, that turned out to be very fruitful, which is, to me, whenever someone says, a physicist says, oh, you shouldn't dabble in unobservables, you shouldn't dabble in metaphysics, I try to point out that that's actually what Boltzmann did. And it can be very fruitful.
Well, to the extent that physics is dependent upon mathematics, and mathematics describes what appear to be very real, non-physical relationships, you're there anyway.
I would say so. I think that's a valid point. I mean, you can certainly say that mathematics is an abstraction, and perhaps we could make mathematical constructions that wouldn't have any physical correlate in the real world. But it's very interesting to see how historically mathematicians have just conjured up these strange ideas like the imaginary unit. And they called it imaginary because they thought it was just something they were playing with that wasn't real. In other words, the
square root of minus
-1. Right. And it turned out that had a physical application, a very, very important physical, many physical applications.
And that, as I understand your work, that has opened up the door for a lot of thinking about the reality of metaphysical realms.
It certainly has. It certainly has, because one of the challenges of quantum theory is that the mathematical objects that it works with have this imaginary character, more generally complex. They're complex numbers, which have both real and imaginary components. And that's one of the challenges in interpreting it, because in general, a real observable empirical quantity always has a real, like I am about 2 meters from you. I'm not 2 plus I meters from you. Right. So in ordinary space and time, we always have real parameters that we use to describe our relationships. But in quantum theory, we have these complex objects. So the question is, what do they refer to?
Well, and I know I don't want to push you too far, but I certainly know that there are some thinkers, including the great physicist Wolfgang Pauli, who began exploring the idea of these imaginary numbers representing realms of consciousness.
Well, as soon as you say, it appears that the quantum formalism is referring to something sub-empirical, at least in part. Well, the mind is something that's sub-empirical in the sense that we don't go, hey, I'm looking at your mind now. I've got, we don't use our 5 senses to locate a mind in space and time. It's something that is not manifest as a space and time object. So it's natural for someone to explore those connections.
And yet each one of us, even if we can't look at our own mind, we know it's there.
We're experiencing it in an inner way. Mm-hmm. It's not in an external way. Yeah. So that raises the question of, could the quantum formalism be referring to some inner dimension, if you will? Mm-hmm.
Many people by now have speculated on that.
Sure.
There are at least 100 books, I should think,
right,
on that. And I know in your own writing you don't go as far as many other people do, but you're at least opening the door to say we need to look at unseen worlds and try to understand their philosophical implications.
Right, I think so. I think that to be realist about quantum theory, which is what I am, and I'm a realist because I think that if you're not, you can never give any account for why it works so well. Mm-hmm. And to me, that's not the scientific spirit.
Now, you've used the term realist, and I know that has a very precise technical meaning for you. So we only have about a minute or so left, but let's spell that out.
Well, realism about a theory means that you think that the theory is describing something that's real, describing something that exists, independently of any particular person's mind, say. Mm-hmm. So it's not something that is a measure of my knowledge. It refers to something that exists in the world, even if we can't point to it and say, give it space-time coordinates.
Now, in other words, you can be a realist and also acknowledge that there are realms of reality that have valid ontological status, but they're not observable.
Right, exactly. That's what I would say, yes. Mm-hmm. Yeah.
And the particular nature of those realms, well, that needs to be explored maybe by methods outside of quantum physics.
Sure. I mean, to some extent, it's a philosophical exploration. It's analytical philosophy. We're using reason here. Yeah. We want to be consistent with our reasoning, but we also want to not constrain ourselves by assumptions, such as one assumption is the only thing that's real is something that's a space-time object. Mm-hmm. Well, that's a metaphysical position. Yeah. It's not something that empirical science can say is true.
Mm-hmm. Well, Ruth Kastner, this has been very educational for me. We hear so much about quantum physics these days and the paradoxes and mysteries. I think you've helped elucidate some of that. Thank you so much for being with me.
I'm glad. Thank you. It's been a pleasure.
And thank you for being with us.